Okay, now we're going to start up with section 3.3, measures of position. And we're going to start off by talking about standard scores or z-scores. So the z-scores tell you how many standard deviations a data value is above or below the mean for a specific distribution of values. So we've just learned how to calculate the mean, and we've learned how to calculate standard deviations. And now this is going to tell you, like, if you hand me a given data point, how does this compare to the rest of the data, right? So if you got like a 98% in your test, how much better did you do than everyone else? Or, how much worse did you do than everyone else, vice versa. Okay, so to calculate a z-score is pretty straightforward. You take the value that you want to analyze, you subtract the mean, and then you divide by the standard deviation. And of course, for samples, it's x minus x bar over s, and for populations, it's x minus mu over sigma. So here's an interesting example. It says a student scored a 65 on a calculus test that had a mean of 50 and a standard deviation of 10. She scored 30 on a history test with a mean of 25 and a standard deviation of 5. Compare relative positions on the two tests. So just looking at this data, you're like, okay, well, she did better than the mean in both cases, but how much better or how much worse? It's hard to say. So the z-score gives you a way to analyze this. So for calculus, again, she got a 65. So we take 65 minus 50, and then we would divide by the standard deviation of 10. So that's 15 divided by 10 is a 1.5. So she has a z-score of 1.5. For history, we get that z is 30 minus 25 divided by 5, and so that's a z-score of 1. So since the calculus score is 1.5 and the history score is 1, the calculus score is bigger. So that means her relative position in the class is higher in calculus than it is in the history class. So if the z-score is positive, the score is above the mean. If it's negative, then it's below. And if it's equal to, if it's 0, then it's equal to. So z-scores being 0 means you're right on the mean. If it's a positive value, you're above. And if it's negative, it's below. Anything to add there, Karen?
No, just that like the 1.5, what that's saying is that, she scored 1.5 standard deviations above the mean. Compared with history, she was only 1 standard deviation above the mean. So if you think about test scores, you obviously want to be further away from the mean in the positive direction. So that's why like having a larger one is better, because it just tells you that you're more to the right, on a number line.
Right. Okay, and so now we're going to talk about percentiles, which is something you've probably encountered if you've ever gone to the doctor, especially if you have kids. They're always talking about percentiles. But in educational and health-related fields, they use percentiles to indicate an individual's position within a group. So percentiles divide the data set into 100 equal groups. And so you have P1 through P99. And so it's important to note that percentiles are not percentages, right? So in this example, let's say you scored, a student scored 72 out of 100. They would get a 72%. Okay, that's just their score in the exam. But that doesn't tell how they did relative to the rest of the class. So if that raw score of 72 was in the 64th percentile, then that means that student did better than 64% of the people in her class. Okay, so let's go over how to calculate a percentile. So you take the number of values below your data point X, you add 0.5 to that, and then you divide by the total number of values for the data set, and then you multiply by 100. So in example 2, it says that a teacher gives a 20-point test to 10 students. The scores are below. Find the percentile rank of a score of 12. So what we want to do here is we want to scan all the data values and circle all the ones that are less than 12. Okay. So I see here 6, 8, 2, 3, 5, and 10. Those are all below 12. So I think there are 6 values less than 12. We're going to add 0.5 to it. And then following this formula, we're just going to divide by the number of data points. We know that there were 10 students. So that's 6 plus 0.5 divided by 10 is 6.5. And then we're going to multiply by 100. So we get 65%. So that tells us that a score of 12 means that this student did better than 65% of the class. Interesting side note, my son just had his 1-year checkup and he's 97th percentile for height and 87th percentile for weight. So he's taller than the average baby, but he's heavier than the average baby, but he's still kind of lean. Karen's just doing the math in her head, like, who cares? Okay. This is the only thing that's like the parents care about, right? It's how
I know
how their
it's so
kids doing.
funny when parents share all the statistics about like how long their baby was when they were born and like all that stuff. I don't know. Maybe I'll understand it one day.
Yeah. Okay.
Okay. So now we're basically going to go like the other way with what Dr. Insco was just doing in that last example. So now we're going to try to find a data value corresponding to a given percentile. Okay, so I have the steps there for us in the notes. So we're kind of just going to follow those as we go through example 3. So example 3 says, using the scores from the previous example, we want to find the value that corresponds to the 25th percentile. Okay, so step 1 is to arrange the data in order from lowest to highest. So I'm going to take those 10 values from the previous example and jot them down on my paper and put them in order from least to greatest. Okay, and then step 2, we're going to substitute into the formula that you can see up there in that blue box, where it's C equals N times P over 100. Okay, so N is going to be the total number of values. So as we said, there's 10 students, or 10 numbers there. So N is 10. And then P is the percentile for that specific question. So we're finding the value that corresponds to the 25th percentile. So P is going to be 25. So you don't need to like turn it into a decimal or anything. Just keep 25 as 25. And then you just simplify 10 times 25 divided by 100, and that comes out to be 2.5. Now, for step 3, you'll notice that we have 2 options. We're either going to use 3A or 3B. Okay, so Dr. Insko, why don't you tell us which one do you think that we should use according to what's written up there?
Okay, so 3A says if it's not a whole number, then you want to round up to the next whole number. And this is 2.5 is not a whole number, so we want to use 3A here.
Yep, very good. So you just have to look at whether C comes out to be a whole number or not. 2.5 is obviously not a whole number, so we're going to use 3A. Okay, and it says that we want to round it up to the next whole number. So the C value that we're actually going to use will be 3. Now, I'm specifically stating here that you always round up, and that's because even if C came out to be like 2.1 or 2.2, you would still round it up to 3. So it's not like a normal rounding rule. It's always round up. So for any decimal part, you would go up to the next whole number. Now, what that C value is it's just telling you what position data value you want to look for now in your set. So you just want to go back to step 1 and just count over 3 places. So we just want to find what value is in the 3rd position. So you can see that corresponds to the data value 5. So that means that the value 5 corresponds to the 25th percentile.
Right. Okay, and so I'll try to do example 4 now. So using the scores from the previous example, find the value that corresponds to the 60th percentile. So we're going to do step 1 and 2 exactly like we just did. So 1 was list all the data points in order. So we're doing that. And then we're going to take N times P. So that's 10 times P is 60 now. So we're going to get 10 times 60 is 600 divided by 100. So we get C equals 6. And so now for step 3, we're in case B where C is a whole number. So what we're going to do is we're going to count over 6 spots and 7 spots. So we go to C and C plus 1, and then we take the value in between those 2. So we're using 3B, and so we have to take the number halfway between C equals 6 and C equals 7. So count over. C equals 6 corresponds to 10, and C equals 7 corresponds to 12, and we want to take the value halfway between those. So again, you're just taking the mean. So you take 10 plus 12 divided by 2, and you get 11. So that means that a score of 11 corresponds to the 60th percentile. So anyone scoring 11 would have done better than 60% of the class. Does that sound good, Karen?
Yeah.
Okay. Okay, now we're going to do quartiles. I can't remember, am I talking about this or are you talking about it? I can talk about it.
You can talk about it.
Okay, so quartiles are pretty easy. We're just trying to break up instead of doing percentiles where you break it up into 100 different groups, here we're going to break the data up into 4 groups. And to do this, you always just calculate the median values. So the median value for Q2 is what we're going to calculate first. And what that means is you just take all your data points and you put them in order from smallest to largest. And then there are 8 data points here. And so we're just looking for the median value, which means that, again, we're going to cross out the 2 largest, and then the next 2 largest and smallest, the next 2. And then we're left with 13 and 15. We want to take the mean of that. So that's 13 plus 15 is 28 divided by 2 is 14. So that tells us that Q2, the Q2 value is 14, right? And then to calculate Q1 and Q3, we do the same thing, but to calculate Q1, we only use the smallest half of values. And for Q3, we only use the largest half of values here. So to calculate the Q1, we're going to cross out the 5 and 13, and then we're going to take the average of 6 and 12, or the mean of 6 and 12. So that's 18. So that's 6 plus 12 is 18 divided by 2 gives us a 9 for our Q1 value. And maybe the student should pause and try and do Q3. You can pause the video or you can just keep listening. But again, to get Q3, all you're going to do is you're going to take the 4 largest values, cross out the 15 and the 50, and then take the average of 18 and 22, and that's going to be 20, right? And then you're going to divide by, average of 18 and 22 is 20, because you take 18 plus 22 divided by 2 gives you 20. And so that says that Q3 is 20. And then you can use that to calculate the interquartile range. And that just is kind of helps you measure variability, and it helps you find outliers. So the interquartile range is just the middle 50% of your data. So you take Q3 minus Q1, and that gives you the interquartile range. So in this previous example, we would take 20 minus 9, and that would give us an interquartile range of 11. And now that's just me writing all this down. I got ahead of myself. They were talking. So yeah, Q3 minus Q1 is 20 minus 9. That gives you an 11. That's the range of the interquartile. And Karen's going to use the IQR to do some, find some outliers now, I think.
Yeah, so I mean, we previously had mentioned that outliers, it's some data value that just looks like it doesn't belong with the rest of the set because it's either really large or really small comparatively. So like, for example, if we're looking at, the numbers in example 7 there, Dr. Insko, if I were to ask you, which one do you think might be an outlier?
I think that 50.
Yeah, I mean, I think we would all probably agree that if we had to pick a value, we'd probably all say 50 kind of looks a little bit too large compared with the rest of the numbers. But essentially, we're just guessing at this point. Mm-hmm. So we want to actually have like a mathematical way of determining whether a number can, officially be declared an outlier or not. So that's what we're going to look at now. So up there in that blue box, we have the 5 steps. That's the procedure for identifying outliers. So let's go ahead. I'll follow those steps as we go through example 7. So steps 1 and 2, we actually just did on the previous page. So step 1 is to find your Q1 and Q3. So we did that. Q1 was 9, Q3 was 20. And then step 2 is to find the IQR, which is just Q3 minus Q1. We did that as well already, and we determined that was 11. Okay, now step 3, what you want to do is take your IQR and multiply it by 1.5. So we'll do 11 times 1.5, which comes out to be 16.5. Okay, then step 4, you want to take that 16.5 and you're going to subtract it from Q1 and you're going to add it to Q3. Okay, that's basically going to give you like a lower bound and an upper bound on the acceptable values for your data set. Okay. So Q1 was 9, so you do 9 minus the 16.5 comes out to be negative 7.5, and then Q3 was 20, so 20 plus 16.5 comes out to be 36.5. Okay, so that's your range of values. So anything that falls within that range is not considered an outlier. So now you just want to check, all right, are any values from my data set outside of negative 7.5 to 36.5? Well, yes, that's the 50 that we thought. So 50 is an outlier, and it falls because it falls outside of that range.
Okay, cool. Okay, are you gonna talk about this too?
Sure. Okay, so that was the end of section 3.3, and 3.4 is the shortest section by far in this entire semester. It's just this one page right here. And it's just gonna be about what we call the 5-number summary. And we're gonna use that 5-number summary to help us draw what's called a box plot, or I grew up calling it a box and whisker plot. So you may have heard that phrase as well. Okay, now the 5-number summary, what they are is it's the minimum value of your data set, Q1, Q2, which is the same thing as the median, Q3, and then the maximum value of your data set. Now, none of those are, you know, terribly tricky to find, but can we do it in our calculator? Yes. So your calculator will actually do that 5-number summary for you. So it saves you some time. So for example, 8, if you go ahead and put those values into a list in your calculator. So just put them in L1 and then go to one variable stats, run it for L1. And then the list that comes up on your screen, if you actually scroll down to the bottom, just like scroll down a couple of clicks, you'll see that it says like min Q1, here, I'll look at mine. Yep, it says min X, Q1, med, Q3, and max X. So your calculator literally gives you those 5 numbers in the exact order that you want them and everything. So let's see what they are for this example. So the minimum 30, Q1 was 47, median or Q2, whatever you want to call it, is 83.5, Q3 is 164, and the maximum is 296. Okay, so we're going to use those numbers to help us draw a box and whisker plot. So we'll do the best we can when we're doing it by hand. So go ahead, we'll just draw like a number line. And you can label it, you know, however you want if you're doing it by hand. Obviously, you want it to kind of be appropriate for your data. So I did it from 0 to 300 just so I can capture all the data. And then I went by 50s. On Connect Math, I mean, they're going to have the number line there for you, so you're not going to have to, you know, pick those numbers yourself. And then you're going to start out by, hold on, don't go too fast. So you're going to start out by first putting your minimum point, and you're going to draw that as like a dot. So the minimum was 30. So don't do it on your number line. Do it like above your number line. So you'll put a point for 30. And then the quartiles are going to be vertical lines. So Q1, you want to approximate where 47 is, and then you're going to draw a vertical line there. And then you're going to attach the first point to that vertical line. And that's going to essentially make your first whisker there. Okay, and then for the median, 83.5, find where that is, make a vertical line. And same thing with Q3. So 164, that'll be a vertical line as well. The quartiles, they're all going to form the box part. So at this point, you can go ahead and connect all of those nicely, and you see that you now have a box in the middle. And then the maximum is going to be another, you know, point or dot. So go make a dot at 296, and then you'll connect that to Q3, and that'll give you your other whisker. So now we have our box and whisker plot. Okay, now how is this helpful? Well, we can definitely get some information from our box plot. So one thing you can look at if you want to determine like how your data is skewed, you can look at where the median falls in that box. So if it falls in the center, that tells you your data is approximately symmetric. If it falls to the left of the center, that means the data is positively skewed. And if it falls to the right of the center, it's negatively skewed. So how does our median fall in that box, Dr. Insco?
It falls to the left of center.
Yep, it falls to the left of the center of the box. So that tells us that the data is positively skewed. Now, there's another thing you can also look at. So you can also look at the whiskers, or they just call them the lines. But if the whiskers are about the same length, that tells you the data is approximately symmetric. If the right one is longer, the data is positively skewed. And if the left one is longer, the data is negatively skewed. So which one of our lines is longer?
The right one.
The right one. So again, we see that our distribution is positively skewed. So you'll get the same answer as far as skewness, whether you want to use like the median or the whiskers. So either one of those will tell you how your distribution is skewed. So if you want to just click a couple times, we'll put our answer up there.
Oh, okay. I'm supposed to highlight those.
That's okay. But for our final answer, we'll say that the distribution is positively skewed.
Perfect.
And that's the end of section 3.4 and the end of chapter 3.
Awesome. I think I might share a video of one of my graduate students who used box plots when describing gerrymandering, and she was able to use these box and whisker plots to analyze different redistricting maps and show that certain maps that were being employed by parties were like very highly unusual because they were like, you know, there was a 1% chance that they would have been made randomly. So it was like obvious that the parties were picking a particular map for particular purposes, and it could either be to make sure that they have a majority or a supermajority. But a lot of times they were picking them just so that their supermajority wouldn't get broken. Even if the vote was approximately 50-50, they would try to form the maps in such a way that it was much more statistically likely that they were going to keep a 3-2 majority, even if there was like 49-51 against their favor. So, anyways, these box and whisker plots are commonly used.
Local data? Did she do that with local data?
No, she did it. She used the state of Oregon only because of like congressional districts. Like her calculations were based on like how many congressional districts there are, and in Oregon there were only 5, but in Florida there's like 27. So her computations would have been huge if you'd done the same methods for Florida, but she could.
Cool.
Yeah. Sorry. So maybe I'll share that video.